say that it's an honor for me to be invited to speak at this conference to celebrate the life and the achievement of Rodney Baxter. Of course, a lot of my work during my career has been heavily influenced by the ideas and the works of Rodney Baxter. And I have met him once in person, namely at the Baxter 2020 conference, organized to celebrate his 80th birthday. And just from that one encounter, I did get the impression that Rodney Baxter was an extraordinary person. And I'm very grateful to my Australian colleagues for having given me the opportunity to actually meet him and also to visit the wonderful continent where he chose to settle. So the theme of the conference is, of course, I should say, exactly solvable models. And what I will be speaking about is a series of exactly solvable models which belong within the realm of the ADS-CFT correspondence, namely integrable BPS Nahm defects in NF4 super young males. And the talk is based on a paper, partly that I wrote with Adam Chalabi and Chen-Lang Su, and another paper that I wrote with Konstantin Zarembo. Sorry, I have to. I apologize, but I cannot really change. Yes. Okay, it works. Okay, yes, so as I said, what I was speaking about is something which belongs within the realm of the ADS-CFT correspondence. And the ADS-CFT correspondence, it's a common framework for quantum field theory and the string theory. And it comes with a lot of symmetries, both conformal symmetry and supersymmetry. And the way it works is that it identifies a good conformal operator in the quantum field theory with a string state in the string theory. And in some circumstances, both of these objects can then be identified with the eigenstates of an integrable spin chain. And that is how integrable models enter the game. And the main examples of such setups are in 4 dimensions, where the quantum field theory is NF4 super young males theory, and in 3 dimensions, where the quantum field theory is ABDM theory.
Have you scrolled onto the second page, or because we're
yes, I have.
First page still here.
Okay. That's strange. Still first page. What about now?
No, we're stuck on the first page.
Okay, I see the second. That's strange. Now? Okay. It says my screen sharing is paused. So what should I do? Resume maybe? It's still the same?
Yeah, still the same.
I'm sorry about that.
Should we stop sharing and start again? Or?
Yeah, let's try and stop. I'm sorry, I tried yesterday and it seemed okay.
Yeah. Let's try again.
Yes.
Will you try again? Yeah.
Yeah. Okay.
Okay, we've got that page. Just yeah. Now it's all good.
Okay, but now it's not full screen, right?
It looks good, but it's close enough. So
yeah, I think it's a full screen, which made it strange. Can I stay like this?
Yeah, if you're happy to stay like that.
Let me just try once more.
Okay.
Yeah, it doesn't go full screen.
It doesn't go full screen. I see.
Okay, so let me stop sharing. And then let me do it full screen before sharing.
Looks good.
Oh, I went try.
Let me see if I can switch full screen. Yeah, okay, I'm sorry, but I think I have to do it without full screen then. Once more, let me try once more.
Yes.
So is it full screen for you?
No. We can see it, but there's a menu there too.
Okay. Then it's not full screen for you.
But this is okay just now. And that's maybe the best we can do.
Yeah, I'm afraid so. Is it okay with you?
Yeah. That's okay if you can scroll through it, as long as you can.
Okay. Okay, maybe I start again from this slide. One second. Okay, yeah, so as I said, what I'm speaking about is something which belongs to the realm of the ADS-CFT correspondence, which is a correspondence which comes with a lot of symmetries, such as conformal symmetry and supersymmetry. And the way it works is that a good conformal operator in the quantum field theory, it's identified with a string in the string theory. And in some circumstances, both of these can then be identified with the eigenstate of an integrable spin chain, and that is how integrable models enter the game. And the main examples of such setups are in 4 dimensions, where the quantum field theory is n=4 super Yang-Mills theory, and in 3 dimensions, where the quantum field theory is Abelian theory. And this latter correspondence with integrable models works in the planar limit of the field theory. And I will be considering the 4-dimensional case. And what I will be doing more specifically is to introduce a defect, a codimensional D defect in my quantum field theory. And that in the string theory picture corresponds to introducing a probe brain, some higher dimensional membrane, which shares a number of dimensions with our 4-dimensional world. And we also know how this introduction of a defect is described in the spin chain language, namely the defect respectively the probe brain can be described as a boundary state of the spin chain. And importantly, if you take the overlap of this boundary state with a beta eigenstate, then you get the 1-point function of the operator, which is represented by the beta eigenstate. And in some cases, the boundary state can be integrable, meaning that this overlap, this 1-point function, can be computed in closed form. Okay. So, do you see my next slide now?
Yes.
With a motivation?
Yes.
Yes, okay. So, here's a list of motivations why we should study these setups. As I just said, the ADS-CFT correspondence comes with a lot of symmetries, conformal symmetry, and supersymmetry. And introducing the defects constitute an organized or systematic way of breaking some of these symmetries, and they allow us therefore to study the interplay between conformal symmetry, supersymmetry, and integrability. They actually also allow us to test the ADS-CFT correspondence where some of the symmetries are broken. And well, that is not the topic of my talk today, but I can say that all these tests have so far come out positive. What is more related to my talk is that these defect setups, they allow us, using the tools of integrable models, to get exact results for new types of observables, such as 1-point functions in the presence of the defects, and new 2-point functions between bulk and boundary operators. There are also some interesting connections to statistical physics and even quantum information theory. Concepts such as matrix product states and quantum ranges, they naturally appear when we study these defects. And finally, the fact that we can produce new exact results opens a possibility for cross-fertilization with a boundary conformal bootstrap program, which might need exactly our data as input for their efforts. Okay, so here's a more detailed plan of my talk. So I will concentrate on defects which are known as half BPS Nahm pole defects. And I will of course start by describing what these defects are and list the different possible types. Then I will turn to discussing their integrability properties. And here I will in particular focus on so-called Cooker-Witten surface defects, which have so far not been studied very much from the integrability perspective. The fact that I've chosen to speak about these half BPS Nahm pole defects is also that they are supersymmetric, and therefore they can be treated by another exact method, namely localization. And localization actually predicts some very intriguing structure of the perturbative expansion of correlators in these defect theories. And that prediction actually gives us prediction for what we in the ADS-CFT community call wrapping corrections, but which are essentially finite size corrections. And that is something which is still to be determined for these defect setups. And then I will finish by a summary and an outlook. Okay, so Nahm pole defects we can characterize as hyperplanes along which some scalar fields have diverging classical values or webs. More precisely, the fields have to behave in this way here, where r is the distance to the defect. So, to my knowledge, there are 3 such defects in N=4 super Young-Mills theory, corresponding to the 3 possible values of the codimension. So, if the codimension is 1, we have a domain wall defect, and that is characterized by 3 of the scalars of N=4 super Young-Mills theory getting a vacuum expectation value different from 0. The case of D=3, which is a line defect, obviously, you obtain if you insert a monopole, magnetic monopole in N=4 super Young-Mills. And to do that requires to have 3 components of the gauge field potential, having non-vanishing webs, and to conserve supersymmetry, we also need 1 scalar to have a non-vanishing web. And then finally, there are these more novel Cooker-Witten surface defects. For that case, you need 2 scalars with a non-vanishing web and a single component of the gauge field with a non-vanishing web. And I should say that in this case, there's also a dependence on the angle around the angular variable in the plane perpendicular to the defect. Okay. So now when we introduce these defects, we of course break translational invariance, and that means that 1-point functions of operators in the bulk can have non-vanishing 1-point functions. And since we are choosing a scaling of our fields which makes the entire setup of defect CFT, we can also constrain the form of the 1-point functions. They have to take the form given here, where x_perp is the perpendicular distance to the defect, and delta is the conformal dimension of the operator, and C is a new type of structure constant that we have to compute. And due to the fact that some fields have non-vanishing webs, we have non-vanishing 1-point functions already at the tree level. And we find these 1-point functions by taking our good conformal operators and plugging in the classical values for the fields. That is in principle a trivial task, but we have to remember that we need to take the good conformal operators, and to find these we have to diagonalize the Hamiltonian of an integrable spin chain. And here that then gives us the good conformal operators, and I've shown here the mapping between the operator and the spin chain state. It looks like this. And we can formulate the computation of the 1-point function in a nice manner if we introduce a matrix product state in the spin chain representing the defect. And that matrix product state should be the spin chain state given here. It's a sum over all spin configurations. And for each spin configuration, we have a prefactor, which is the trace of the corresponding classical fields. So when we take the inner product between the matrix product state and the beta eigenstate, then this inner product exactly picks out the term in the beta eigenstate which has the same order of the spin states as given here, and then it replaces it with a trace of the classical fields. And that means that it's exactly implementing the procedure up here to compute the 1-point function. And then to get the right normalization, we also need to divide by the norm of the beta eigenstates, as I've written down here, and we get this trivial space-time dependence. And these are the ideas that we want to apply to these, especially Gucker-Witten surface defects. Okay, so here's an overview of the different types of half BPS Nahm pole defects in NX4 superYAMLs. So when you introduce a defect, you also always introduce an extra parameter, and that parameter can be either discrete or continuous. So for the 't Hooft line and the domain wall, the extra parameter is discrete. For the 't Hooft line, it's simply the monopole charge, and in the domain wall case, it's a magnetic flux, which has to be quantized. And in the field theory language, is the size of a certain SU2 representation. The Gucker-Witten defects, on the other hand, they can come both in a continuous and a discrete version. The continuous one is known as non-rigid defects, and the discrete one is known as rigid defects. And all of these defects, they correspond in the string theory picture to, as I said, a certain probe brain that we insert in the usual ADS 5x5 string theory background. And we have, for the domain wall, it's a D5 brain, for Gucker-Witten surface defects, D3 brains, and for the 't Hooft line, a D1 brain. And in each case, the brain has a particular geometry. It has a geometry which is a product of a lower dimensional ADS space, which lies inside the ADS 5 part of the geometry, and a lower dimensional sphere, which lies inside the sphere part of the background geometry. And then in each case, the boundary of this smaller ADS space is actually what constitutes a defect in our quantum field theory. Okay, so here I have given the global conformal symmetries of the different Nahm pole setups. So you can see that the domain wall and the 't Hooft line, they have the same symmetries, whereas those of the Gucker-Witten surface defects are different. And finally, the background field, well, it's of course a matrix field because all fields are adjoint in N=4 superYAMLs, but this can be a commutative or a non-commutative field, that is a diagonal or non-diagonal matrix. So for the domain wall, it's a non-commutative matrix, an SU2 generator. For the 't Hooft line, it's a diagonal matrix. And for the Gucker-Witten surface defects, we can have either situation, commutative for the non-rigid and non-commutative for the rigid defects. Okay. So this is what the Gucker-Witten defects look like in more detail. So as I said, there are two scalar fields, two real scalar fields which get webs, or equivalently one classical one. And the classical field take this form here with some parameters, some betas and gammas, which are real, and each complex number, beta I plus I gamma I, can appear a certain number of times along the diagonal. And the space-time dependence is given by this 1/c, which is related to the polar coordinates in the plane perpendicular to the defect in this standard way. Then there's also a classical value for the component of the gauge field potential. It looks like this, where the alphas are now real and periodic. So that's the ordinary commutative non-rigid case. The rigid case, it appears if you require the fields, of course, to fulfill the classical equation of motions and the equations which give you supersymmetry, which are called the Nahm equations. But then you also assume a logarithmic scaling. Then you find that this is a possible classical field configuration where it's necessary that these T's here are non-commutative and have to fulfill the SU2 algebra. So these are generators in some irreducible representations of SU2. And it can in principle have any dimension. And then this rigid case, it corresponds in some intricate way to the limit of the ordinary case where you send all the betas and gammas to 0. Okay. So here's what it looks like from the string theory side. So as I said, it corresponds to a certain probe brain which is embedded in the ADS5 times S5 background. So here is a metric of the background with the ADS5 metric here, and then this is supposed to be the metric of S5. And the radius of ADS5 here is y, and the boundary of ADS5 is at y equal to 0. So in this background, I then put a D3 brain with 3 coordinates, which I take to be these, with 4 coordinates, sorry, which I take to be these 4, which belong to the set of ADS coordinates. But then I also, of course, I have to provide some embedding functions which tell us how this deep brain is embedded in the background. And the way it's embedded is that it sits at a point theta equal to pi over 2 on the 5 sphere. And then it also, it wraps a sphere given by this angle phi on the 5 sphere. But that angle, or that sphere, or circle on the 5 sphere is linked to a circle inside ADS given by this angle psi. And the relation is this linear one where phi 0 is some integration constant. And then you can also see that the sphere that the brain wraps inside ADS5, its radius, small r, it grows as we move towards larger values of y, that is when we move more inside ADS. So the brain is cone-shaped in ADS. And this, the shape of the sphere or the circle is also determined by some integration constant kappa. So we have 2 integration constants on the string theory side and 2 on the gauge theory side, and they are related via this equation here. And you see there's nothing discrete here, everything is continuous variables. And you can also see from here that the rigid case where beta and gamma are sent to 0, it corresponds to this parameter kappa going to 0, which means that the sphere or the circle inside ADS wrapped by the D3 brain shrinks to a line or to a point, and but the circle wrapped on the S5, it stays a circle, an extended circle. Okay. So here I've summarized the 3-level integrability properties of the Gucker-Witten surface defects. So what you do to investigate the integrability properties is to start from some small subsector of fields, look for integrability, and then extend the amount of fields you include in the analysis order step by step. So the simplest sector is a so-called SU2 sector consisting of only 2 complex fields. And it turns out that the ordinary Gucker-Witten defects have trivial one-point functions in that sector, meaning vanishing ones, whereas the rigid ones have non-trivial one-point functions, but they actually coincide with the one-point functions which are known from the domain wall case and which are integrable for all values of the parameter k, which was the size of the SU2 representation, as long as k is larger than or equal to 2 at least. Okay, then if you move on to bigger sectors, you find for the ordinary defect that you still have integrability if you involve all scalars, and that for all values of beta I and gamma I. And here the overlaps actually also coincide with some overlaps which are known for another case. However, if you move on to what is known as the SL2 sector, where you allow a complex scalar plus a covariant derivative, then you find that the model is no longer integrable. So there's no hope of extending integrability to the full theory in this case. The situation is a little bit better for the rigid defects. Here we find that the one-point functions are integrable, both in the SO6 and the SL2 sector, at least when the size of the representation matrices is equal to 2. So in this particular case, in this corner of parameter space, we have the chance to extend integrability, or we have the chance that integrability extends to the entire theory. And the way in which we test for integrability in these setups is that we test if the boundary state of the spin chain is annihilated by all the odd charges of the spin chain. This is a criterion which has shown to work as an integrability test, and it was suggested by Potsky. Then if we find indications for integrability, we move on and solve what is known as the KT relation to find the so-called K matrix. And then from that, by a recursive strategy, we can actually determine the overlap. And all this is something which was worked out over many years, and I would say culminated with a paper from last fall by Thomas Gomborg. And here I show you what comes out of this analysis. So what I show here is the tree-level one-point functions for the rigid Gukov-Witten defects for the integrable case where k is equal to 2. So this is what the one-point functions look like. So they have the form which is known from other studies of one-point functions in similar setups. Namely, it's expressed entirely in terms of the Godin determinant, or rather the superdeterminant of the Godin matrix, and then, importantly, some Baxter polynomials. And there is one Baxter polynomial for each node of the thinking diagram of the underlying symmetry algebra, which is here SO6. So there are three Baxter polynomials, but for some reason only one of them appears in the overlap formula. And here it's understood that the overlap is only non-vanishing if the beta roots of the beta eigenstate come in pairs, and they have to come in pairs in such a way that the roots at the outer nodes are paired with each other, and the roots at the central node are paired among themselves. So this you can contrast with the domain wall case. It's also something which is based on the symmetry algebra SO6, and therefore the overlap formula is expressed in terms of three Baxter polynomials. But it takes a completely different form, and also the pairing condition is completely different. In this case here, the roots have to come in plus minus pairs at each node of the thinking diagram. And this symmetry pattern is also something which has an understanding, and which is also summarized in this work by Thomas Gomborg. Okay. But let me stress that this was only a statement about tree-level integrability. So what happens if we want to go to higher loops in the quantum field theory? Well, we are at different stages for the different types of domain walls, of defects. In the domain wall case, we know that from the string theory side, the boundary conditions are integrable, even with the presence of these classical fields. And it has been possible to derive an asymptotic all-loop formula for the overlaps, meaning a formula which is valid if the operator is long enough. And that was done by the two groups given here, and being long enough means that the formula is valid up to the order lambda to the L, where L is the length of the operator. For the Gukov-Witten surface defects, we know from an analysis of Dickel and Oos that the string boundary conditions are integrable, at least when you don't have any VEFs. And from our analysis, we know that the field theory or the entire setup can only be integrable if k is equal to 2. Finally, for the 't Hooft line, we also have the same result, that the string boundary conditions are integrable when there are no VEFs. And here there's a partial asymptotic all-loop formula. It's determined up to a certain reflection phase, which could not be fixed by the symmetry arguments. So we are at different stages, but it probably depends on, or it relies on the fact that we have been studying these defect setups for a different amount of time. But what is missing in all cases are finite size corrections, or what is known as wrapping corrections in the ADS-CFT community, which are, in the quantum field theory language, corrections which come from Feynman diagrams which wrap all around the operator that one considers. Okay. And as I said, I chose to consider supersymmetric defect setups because in that case one could actually get some information about wrapping corrections from another exact method known as localization. And let me, as an example, consider the 't Hooft loop, the codimension 3 defect. And let me consider the one-point function of a protected operator of the simplest type, namely this one, which involves just the trace of a single complex scalar. Such a setup with a one-point function of this operator in the background of the whole loop is again a supersymmetric setup, and one can use localization to compute it exactly. And then knowing this result, well, actually, we cannot compute this result exactly. We can compute the similar result if the defect takes the form of a Wilson line. And then we can use what is known as S-duality of n equals 4 super Yang-Mills theory to get a prediction for the same one-point function in the background of the to Hoof line. And that's because this S-duality, it interchanges magnetic and electric quantities with a simultaneous change of the coupling constant. But if you go through this procedure of S-dualizing the Wilson loop result, then you end up with this prediction for the one-point function of the chiral primary up here in the background of the to Hoof loop. Here, little r is the distance from the to Hoof loop, and lambda is the coupling constant of the field theory. And the theory and the result becomes even nicer if you uniformize it, introducing Zukovsky variables, which are given in this form here. Then the expression for the space-time independent part, CL here, can be written as a sum of two terms, which apparently have different origin, and people with experience from ADS-CFT would expect that the black part here comes from regular, that is non-wrapping contributions, and the blue part here comes from wrapping contributions. And that's because the black part here, it starts out as the order lambda to the minus L over 2, which are basically comes from a normalization. And the other term, it starts out much later at an order which is expected for these wrapping corrections, namely lambda to the power L over 2. And there's also a gap between the two types of contributions, which I can illustrate by explicitly writing out this expression for various values of L, the length of the operator. So here I've written out these one-point functions for different values of the length, which is a subscript here. And I have stripped off the space-time dependent factor. So you obviously see the two types of terms here. And if you stare at these expressions, you see some peculiar features. Namely, if the operator has an odd length, then the series truncates after a few terms. And even if it has an even length, it truncates the part which does not have to do with finite size corrections. And this is actually very surprising, because this is an exact result which is supposed to be valid to all orders in perturbation theory. So there's some kind of strange truncation going on. And it appears to be a phenomenon which is seen for all these defect setups. If you consider domain walls, then actually all these odd one-point functions, they cancel. And for the Gutkov-Witten defects, all the wrapping contributions cancel, and you have the same truncation of the non-wrapping part. And finally, for the Coulomb branch of n equals 4 super Yang-Mills that you will hear about later from Kristjansen Zarembo, then you have no regular contributions at all, possibly just some wrapping corrections. Okay. So it's easy to write down a closed expression for the non-wrapping corrections. So it takes this form here. There's a perturbative series which terminates at an order which is the integer part of the length of the operator divided by 2. Then there's this field theoretical factor and a combinatorial factor in front. And this I would ideally like to show you how to recover by quantizing around the monopole background. Because it's easy to recover this first coefficient, it's just plugging in the VEFs, but to recover the rest, then one should actually quantize around the non-trivial background and set up the perturbative program and do an honest field theoretical computation. I'm not sure I will have the time for that, but let me mention that one finds exactly the same structure for the domain wall defect with this field theoretical factor and the same combinatorial factor, and then something with a little bit more structure, which involves some Bernoulli polynomials. So these perturbative series we can understand completely. But in the future, we would like to understand the wrapping interactions in the same detail. Am I running out of time or?
Yeah, we're getting into it.
Okay, so let me just say that from explicitly quantizing around the monopole background, then it's a major operation which involves diagonalizing a very complicated mass matrix which mixes the various fields of the theory. Then one, after a long computation, arrives at the result that this phi theoretical factor in the expression for the non-wrapping part of the corrections actually is the value of a simple tadpole diagram. And using that information, we can completely understand what this non-wrapping part of the one-point functions are. Namely, they come from Feynman diagrams where you simply, for a given n, insert n tadpoles, and then this combinatorial factor simply tells you how many times you can do that for an operator of length L. So if you cut open the operator like this, then you have to contract nearest neighbors point to form tadpoles, and if you don't contract the first and the last point, then you can do it in this number of ways, whereas if you contract the first and the last one, then you have only n-1 contractions left that you can do in this number of ways. So this tells us that this perturbative series, the non-wrapping part, it gets contributions only from what we could call flower diagrams with a varying number of leaves, which is very surprising because a priori we would expect contributions from numerous diagrams with internal vertices. And I, in principle, did that for the de Hoof loop, but the same phenomenon is observed for the domain wall and for the Hooker-Witten defect, where there, by the way, are no wrappings. Okay, so that takes me to the conclusion and the outlook. So we have at least 3 examples of these defect CFTs, which can be amenable to several exact methods: localization, integrability, and potentially bootstrap. We have done the quantization around the classical waves for all 3 cases. We have studied them by localization and found this intriguing structure of the perturbative expansion. And now the scene is set for finding the final part, namely the wrapping corrections. So thank you very much.
Thank you, Charlotte. We can have a quick question if anyone online wants to jump in with a question or comment. They just have to unmute themselves. Is there anyone here?
I have a simple question,
Yes,
Charlotte.
Andreas.
You say you want, in the end, you want to use integrability for solving something. I mean, what is it what you are interested in mostly? I mean, how do you like to use integrability?
I would like to find an expression for these one-point functions which is valid at all loop orders in the phi theory, both and valid still not only perturbatively but also non-perturbatively. And that is what I'm working at. I'm starting at tree level, using the tools of integrability to get these closed formulas involving the Baxter polynomials. Then you can move on to higher loops by using a kind of integrability bootstrap, making use of unitarity, crossing, and whatnot. And then on top of that, you need to be able to take care of these finite size corrections, for which you would need some kind of TBA or quantum spectral curve. And this is somehow where we are now.
Okay, thanks again, Charlotte. We need